In this video, we're going to begin our discussion with goodness of fit tests. In previous chapters, we introduced statistical methods that can be used to test hypotheses regarding a population parameter such as p or mu. Often, rather than being interested in testing a hypothesis regarding a parameter of a probability distribution, we want to test hypothesis regarding the entire population distribution. So methods for testing such hypotheses will be discussed in this section. So I've written out a couple of examples we'll take a look at in a couple of minutes. So the method for testing these types of hypotheses use the chi-square distribution. If a simple random sample of size n is obtained from a normally distributed population with a mean and a population standard deviation given, there is the formula that has a chi-square distribution with n-1 degrees of freedom, where s squared is a sample variance. So characteristics of the chi-square distribution. 1, it is not symmetric. 2, its shape depends on the degrees of freedom, just like student's t distribution. 3, as the number of degrees of freedom increases, it becomes more symmetric. And 4, the values of chi-squared are non-negative. That is, the values of chi-squared are greater than or equal to 0. All right, the goodness of fit test. It's an inferential procedure used to determine whether a frequency distribution follows a specific distribution. So, in other words, does the theoretical distribution match with the sample distribution? So the idea behind testing these types of hypotheses is to compare the actual numbers of observations for each category of data with the number of observations we would expect if the null hypothesis is true. If a significant difference exists between the observed counts and the expected counts, we have evidence against the null hypothesis. So, let's write out the null and the alternative hypotheses for the examples below. So here they give you a particular distribution of peanut M&Ms. The null hypothesis says this distribution has not changed. So let me write this out now. So the color of peanut M&Ms follows the manufacturer's stated distribution. Now, the alternative hypothesis says that the distribution is different than what is stated. So let me write that out now. Okay, let's take a look at the next example with a fair die. If a die is fair, I would expect the probability of rolling a 1 to be exactly the same as rolling a probability of a 2, so on and so forth. So here's how I would write the null hypothesis for this. So P1 is equal to P2, which is equal to P3, so on and so forth. The alternative hypothesis tells me that one of these proportions is going to be different from the others. So let's write that out now. So at least one of the proportions is different from the others. So again, it's not our job to be able to figure out which one is different, and in fact how many are different. It's either going to be nothing changes or something does change. So a goodness of fit test uses expected counts. Expected counts are simply extensions of expected values. Well, recall the expected value was this. All right, so suppose there are n independent trials of an experiment with k greater than or equal to 3 mutually exclusive possible outcomes, and let P1 represent the probability of observing the first outcome, and E1 represents the expected counts. We can continue with this with P2 and E2, so on and so forth. So the expected counts is given below. So, in other words, the expected count for each category is the number of trials of the experiment times the probability of success in that particular category. Okay, let's take a look at an example. So, according to the manufacturer of M&Ms, 12% of peanut M&Ms in a bag should be brown, 15% yellow, 12% red, 23% blue, 23% orange, and 15% green. A student randomly selected a bag of peanut M&Ms. He counted the number of M&Ms that were in each color and obtained the results shown in the table below. Determine the expected counts. So let's write this out. All right, before anything else, let's add up the frequency. So if I add these 6 numbers together, I get 400. So let's start with the brown. So the brown, that should be 12%. So it's 12% of 400, and that gets me to 48. Next, the yellow, that's 15%. So that's 15% of 400. That is equal to 60. Red is also 12%. So that, again, that's 12% of 400. That's 48. The next is blue. That's 23%. So 0.23 times 400. That's going to be 92. The orange is also 23%. So that's also going to be 92. And green is 15%. So that's 0.15 times 400 is equal to 60. Those are our expected counts for this example. So, the goodness of fit test. To test a hypothesis regarding a distribution, use the following steps. Write out what the null and the alternative hypotheses are going to be. Decide on a level of significance alpha depending on the seriousness of making a type 1 error. Perform the test. The conditions in this section we'll need to check is calculate the expected values, and we need to verify these 2 conditions. All expected counts are greater than or equal to 1. No more than 20% of the expected counts are less than 5. Right? And we'll use technology to obtain the p-value. Just like everything else up to this point, if the p-value is less than alpha, we will reject the hypothesis. And then, of course, state the conclusion. And I've listed out the test statistic for goodness of fit test. But again, we'll be using the calculator to help us with this and not use the test statistic. Keep in mind, goodness of fit tests are used to test hypothesis regarding the distribution of a variable based on a single population. If you wish to compare 2 or more populations, you must use a different test, which we will talk about in the next section. Okay, let's go back to our peanut M&M example. Now, before anything else, I need to be able to write the expected counts. So I'm going to rewrite the expected counts for this problem again below. Okay, so those are written below. Now, let's go through the requirements. Right? Number 1, all expected counts are greater than or equal to 1, and none of these expected counts are less than 5. That's good news for us. So let's write out the conditions now. Okay, now let's write out the null and alternative hypotheses. So I've already written that out earlier, so I'll rewrite them now. Okay. Now that we've written out the null and the alternative hypotheses, we need to put this into the calculator. So there's going to be 2 columns of numbers we're going to have to put in. The observed is going to be L1, and the expected counts is going to be L2. So now let's go to the calculator and put in the values for L1 and for L2 into the calculator now. Okay, so you can see I put the observed in L1 and the expected counts in column L2. So now, how do I put this into the calculator? Hit Stat, highlight Tests, and we're going to look for chi-squared goodness of fit test, which is going to be letter D. Hit Enter. So the observed is going to be L1. The expected is L2. Now the degrees of freedom, remember it's the number, the different data values minus 1. Well, we had 6 different colors, so 6 minus 1 is equal to 5. Highlight Calculate and hit Enter. So the p-value in this particular case, rounded to 4 decimal places, is going to be 0.6130. So let's put this on the paper now. So on the paper should be chi-squared GOF test right parenthesis L1, comma, L2, comma, remember, 6 different colors minus 1, that's going to be 5, and the p-values rounded to 4 decimal places. So clearly this is not less than 0.05, so we will not reject the null hypothesis. So let's write out the conclusion in the context of this problem now. So there is not sufficient evidence at the alpha equal to 0.05 level of significance to conclude that the color of peanut M&Ms follow a different distribution.